Good morning, everyone, and thank you very much for inviting myself and Lee Brenda. We've both come from the other side of the border. Lee and I have both worked both as consultants and as researchers. And so we've gotten to work a lot with resource management agencies in the United States. And we've gotten to deal with them addressing a lot of different issues. So you've heard a lot about some of those issues today. Here's just a brief list. And we get asked a lot of questions. Now, the questions that get asked depend on what resources you're managing, where you're managing them, where you are. So here you probably have a somewhat different list of questions. These are the sort of things that we get asked a lot in the Pacific Northwest. There's a lot of concern about riparian buffers, about the effects of roads on hydrology and sediment production, about protecting aquatic habitat, identifying where salmon spawning occurs, for example, where salmon rearing occurs, and making sure that we maintain the processes that create and keep that habitat in good quality. We have a lot of concern about slope stability and landslides. And these days we have a lot of concerns about water temperature. So these are the sort of things that we get asked, and we know from experience that we're dealing with systems that are complex. So I put this up here not to go through how to show you how it works, but just to indicate that once we start thinking about how the systems we're trying to understand and trying to anticipate the consequences of our actions on, we find that there are a lot of pieces, a lot of interacting pieces that work over large timescales and large distances, so that once we try to put together a conceptual model to anticipate how everything works together, it gets kind of complicated. And well, we used to do this. We'd stand around like the guys in this picture, looking down over a landslide scarp and scratching our heads, and we'd surveyed up and down hill slopes, up and down stream channels. We draw lines on maps. We looked at air photographs. I've about gone blind looking through the binoculars on stereoscopes. And we work to try to figure all of this out. We've come up with conceptual models. We've come up with numerical models. We have equations. And now, as we've progressed, using all of the sorts of data sources and the tools and the computational facilities we have now, we're trying to move beyond drawing lines on maps to drawing lines with computers. And we've used a number of ways to talk about this, digital landscapes, hydroscapes. Right now we're using the word virtual watershed. But we're really trying to find a way to utilize the digital tools and all the digital data we have to figure out how things work and how they interact with the things that we as humans are doing on the landscape. So I think of a virtual watershed as a digital environment where the landforms are linked with physical and biological processes in the context with the activities and the infrastructure that we pose on the landscape. Now, when we build it, when we're trying to think of how to put all of these tools together, we want something that's going to be spatially explicit, because we use our eyes looking at things to really figure out a lot about how the world works. So we want to be able to visualize these relationships. And you saw some great slides this morning of the very effective use of graphics to show complex processes and to make them understandable. So we want to be able to visualize things so you can see patterns, identify linkages. And of course, nowadays everything is computer-based. But that's great, because the computers can do so much more than we were able to do with our lines on our maps. We can link everybody's models. We can link everybody's data. So we're trying to find ways to capitalize on the work that everybody else is doing, so that we can all share information, share the analysis tools that we're building, and then build on top of each other's efforts so that we can improve on all that. Well, we want to be able to simulate interactions. We want to know what happens, or what might happen if we do some action or we don't do some action. What happens if we build a road here? What happens if we put a harvest unit here? We want to look at different scenarios, and we want a way to do this consistently, so that if different people are doing an analysis, they get the same answers. If we do analyses in different places, we know how to compare them. And the way that we've been then trying to link all of this, these digital representations of the landscape so that people can use them, is to build an interface with the GIS. So that you have a way to easily share data, to share the tools that are being developed, and everybody has a common methodology for doing so. So here are this is continuously evolving, but we've developed a methodology that we use to try to set up a platform for linking data and tools. And these are the components of it. It starts with a digital elevation model. It's something that Chris talked about a lot, the ability to figure out where water flows or anything else that's flowing with the water moves across the landscape. So you start out with some digital representation of elevations. You can use that to figure out topography, flow directions. You can use that then to figure out where the channels are, to build the river networks, as was shown with the wet areas mapping. Now we want to go take those digital representations now of the river networks that are derived from the topography and look at how everything's linked together, to look at how points on the hillside are linked to the points in the river. And we want to do this because the processes that operate on the hillsides are often somewhat different than those that are operating in the rivers. We want to establish these connections, identify the processes and the rates by which water, sediment, wood, nutrients, by which everything moves off of the hill slopes into the rivers and then through the river network. We want to then discretize, make things into small usable pieces that we can assign attributes to. Identify landforms. This is something called object-based analysis. So we divide the whole landscape into unique terrain items, for example, into landforms, and have ways to attribute them, figure out how they're related to each other, and then link all this together. So this gives us a platform on which to attach models, attach data, figure out how they work together, get them to talk to each other, and then spit out files that you can display in a GIS. So it's a way of taking these complicated boxes and things that, you have these big computer programs, and putting them all together so that you end up with maps, animations, graphs, and things that you can actually use. Now, like I said, we're trying to use a GIS as the interface. So Lee is going to talk more about this in the next talk. So we've got this digital representation, but we need a way then for people to use that. And that's something we're calling NetMap right now, is a way to translate between all of this digital stuff and a way for people to look at it on computer screens and to make maps. So I'm going to give you some examples. And I didn't really know what to choose, what to examine for this talk. So I've chosen some things I hope will illustrate what we mean by coupling models and data. The underlying data structure, as we've said, the underlying thing is the hydrography, the river network. That is what integrates everything together. So the first thing we have to do is take the DEMs, and as Chris was describing, hydrologically condition them and build a river network. And this is a great example of where we could learn from each other, because we're solving the same problems that are being solved to build the wet areas mapping. How do you build all of this stuff, breaching and filling? We have to solve the same things. And there are groups all over the world working on the same thing. So we really need to capitalize on each other's efforts and learn from each other's mistakes. But here's an example of something that we've been working with a number of different agencies in Alaska to update the hydrography for the state of Alaska using newly acquired elevation data. When we do this, when we trace out the channel networks, our goal is to extend the network through the channels as far as we can, because a lot of people have different reasons for trying to identify channels. Sometimes it's important to know where you have ephemeral channels, and we'll look at an example of why that's so. So it's good to be able to take another model or another data set and then hook it up with this hydrography that we've designed, or that's been extracted from the DEMs, to then come up with a channel classification. And here's an example looking at the probability of perennial flow. So that's something we've done with the state of Washington to look at the probability, or first of all, to identify where headwater channels exist. So we're looking at channels now that have no fish, that feed into fish-bearing waters, only for forested areas in eastern Washington. So this was a multi-year field effort, which then was translated into a statistical model to predict, based on landscape attributes, what the probability of perennial flow is. And this is important for the state because our forestry regulations have different buffer sizes depending on what type of channel you have. This way we now have an estimate of where we have channels that we need to buffer. Another aspect, and this is a reason that we need to trace channels way beyond the perennial extent, is in assessing landslide risk. So we have a lot of timber operations on very steep country. We also have a lot of people building houses and roads in a country that is landslide prone. So we need a way to couple that data with existing or to be built models to predict slope stability. So here's an example of a model that was developed to predict landslide hazards, the landslides associated with shallow failure of slopes on these steep, of soils on these steep slopes. But that can also then be coupled with a transport model so that we can then look at what is the probability, we can make estimates of the probability of having landslide impacts for all of the streams in an entire channel network. Now this is used then to anticipate where fish habitat is at risk, or where we need to protect wood sources that might be taken by landslides into stream channels to provide fish habitat. So there are a lot of different ways that hazard assessment gets pulled in, and now we're realizing more and more that we need to look at landslide risk and hazard assessment in terms of public safety as well. I'm also going to describe now forest roads are another important aspect of our land use, which is another thing that you can just drape onto a DEM. And a lot of models have been developed for looking at the hydrology of forest roads, for sediment production from forest roads. So this sort of a virtual landscape, a virtual watershed platform gives you a really nice way of tying those things together, of looking at them in conjunction with all of the other pieces that you want to analyze. And I'm just going to show an example for a little watershed in Northern California. Here's a digital elevation model, shaded relief image created from that, a channel network that was derived from that digital elevation model, and I hope it was verified with some field data so that these are actually representing channels that carry water. Here is a road network that exists on top of that in that landscape. And this is a basin that is managed for industrial timber production, so it has a pretty dense road network. Here are all of the drainage structures that have been installed on those roads to try to protect the roads so that they don't get damaged during rainstorms, and to ensure that the roads are not dumping excess water and excess sediment into the stream channels. But how effective are they? Well, we can couple that road network draped on top of the DEM so that we can extract all of the information that needs to go into a model, a hydrologic model for roads, and predict or make an estimate of how much water associated with any given storm or any given time period is actually flowing off of the road network and directly into the channel network. We can also then take that information and tie it together with a sediment production model for roads. So we can estimate for a given set of storms or a given time period, a given traffic level, a given surface composition of the roads, how much sediment is being produced. Now, since we've already got that coupled with a hydrologic model, we can then transport that sediment into the stream channels. So now we have a way of tying the landscape, the roads, the hydrology, to what the effects of those roads are, both on the hydrology of the channel network and sediment delivery to the channels. But since we have all this put together now, we can start to use it in a planning context. We can look at, apply these models to identify where in this road network, if you were to add drainage structures, where would you put them to capitalize or to minimize, to maximize the reduction in sediment and water delivery to the channel network. So we can model these things with existing models now to provide guidance on where you are going to improve your road network, or likewise, where you might do maintenance to improve the surfacing on the roads to minimize the sediment delivery to the stream channels. So these are just some examples of how you can take existing models or develop new models, couple them together within what we've been calling a virtual landscape to make useful, or what we hope are useful predictions. These are examples that people have actually been using. Lee will give you some more focused examples, but that is what a virtual watershed is.